elites. I hope this evening or afternoon finds you happy and healthy and ready to do a little bit of math. We are going to real quick take another look at our learning target 6 from Unit 1, deriving exponential and logarithmic expressions. Now in class today we started this briefly, but I just want to real quick have a review for you in case some of you are a little bit confused. Then we can dive right in tomorrow. So let's just do a quick review. Today in class we said the derivative of e to the x is e to the x. And the derivative of natural log of x is 1 over x. However, if this exponent or this denominator becomes a little more gutsy, maybe we have a function in the exponent of our e expression, this derivative becomes e to the f of x times the derivative of that exponent. So the exponent is where your guts are hidden. Same thing here. If this becomes a little bit more complicated expression, then we have to still use our rule of natural log derivatives, 1 over f of x times f prime of x, which would be the derivative of our inners. Okay? All right, let's just do a couple examples with those before we move on to anything else. So, take a quick look at natural log of sine x squared. Let's remember this squared is only applying to the x term, not the whole sine x term. So if we use our natural log derivative rules, we're going to go 1 over that quantity times the derivative of this quantity. So let's remember we're going to have the derivative of sine is cosine of the same quantity that we started with when we had sine. And then we have to derive that quantity, which is 2x. So don't forget, when you're doing the chain rule, you keep working inside that chain until you are all the way inside your expression, from outside in. Okay? So I'm just kind of rewriting this a little bit. You could, if you wanted, write this as cotangent x squared times 2x. Okay? Okay, let's try an e1. So we've got the derivative of 3e to the root x. Well, this constant multiplier stays there. And e to the root x derivative, remember e for easy, but what becomes a little more complicated is that you have to derive the exponent. That's our gutsy part. So that we all know is 1 over 2 root x. So we have 3e root x over 2 root x is our derivative. Okay? All right, let's try another one here. Okay, so I kind of put a bunch together because why not? You guys are ready for it. This is going to involve product rule. Those of you who remember the u and the v. Product rule, remember, is the derivative of u times v equals u prime v plus uv prime. Remember, you do not just derive this and derive that and put them together with multiplication. It's more complicated than that. All right, so let's try this. So u prime is going to be oops, sorry about that. Let's go ahead and just rewrite this so we have proper notation. So we know the derivative with respect to x of e to the cosine x times natural log of x squared plus 2x. That is going to be u prime, so I'm going to derive that part. That's e to the cosine x. E for easy, just rewrite it, and then times the derivative of the exponent, which is the opposite of sine x. And then I'm going to repeat my v, ln of x squared plus 2x. Gets a little messy here, I know. Then I'm going to add my uv prime. So let's just put in our e to the sine x. Oops, so sorry. That should be e to the cosine x. That's my u. And then I'm going to derive my natural log expression. So that becomes 1 over x squared plus 2x. But remember, you have to derive the inners of this natural log. So I have times 2x plus 2. Now, of course, I could just rewrite this and put the 2x plus 2 on the top if I want to. Okay. And there is your derivative of that expression. Now again, we can find a tangent line approximation. We can find a slope of a tangent line. We can find the instantaneous rate of change of this function that we started with by plugging any x value in. Okay? All right. Let's go to this now. So this is a little bit different. We had the derivative with respect to x of e to the x equals e to the x. But in class, we tried to graph this derivative, and we found that the derivative with respect to x of 5 to the x is not equal to that. Just repeat it. So let's figure out what that will be. All right, well, here we go. We're going to stick a log like you guys said to do in class. Just like last year, we do that so this exponent can get out of the exponent. We want to bring that in front. So we stick a log, and remember that just came from our exponent rules that said, oops, if we have natural log of anything to the x power, I can just bring that in front. So I end up with natural log of y equals x ln 5. Okay, now what we're going to do is we're going to derive both sides. Just like we can multiply both sides by 2 or divide by 2 or add 10 to both sides, we could derive both sides. So what you need to remember is this guy right here, and this is the hardest thing for people to wrap their brains around. That is just a number. So for instance, if I asked you to derive 10x, you would tell me that dy dx is 10. In the same way, if I asked you to derive, so let's say we're going to derive both sides here. If I asked you to derive x ln 5, this is your number times x, just like this was 10 times x. The derivative is just going to be the number in front of x, ln 5. Now this side's a little bit more complicated. We're deriving in terms of x, don't forget. So what I'm doing is think about it this way. You could think about this rewritten as the derivative with respect to x of ln of f of x, right? We could write y as ln of f of x. So think about what we did with that derivative. We said 1 over, or what we did with that function, 1 over f prime of x times the derivative of the inners, which equals the same thing that we had on that other side there. Okay, well, let's keep going with this. I'm just going to write this as f, instead of writing f prime of x, if you don't mind. No, we can keep it that way. Let's just keep it f prime of x over f of x equals ln 5. Well, my goal is to get what f prime of x is. Remember, that's the same as dy dx. So I'm just going to multiply by f of x on both sides. So now those cancel, and I have f prime of x, also known as dy dx, equals ln 5 times f of x. Well, if we go way back to the top, here is our f of x. Remember, we could say f of x is the same as y which equals 5 to the x. So let's go ahead and plug that in. So we have dy dx is going to equal ln 5 times 5 to the x. So what we've just figured out is that if you have the derivative of 5 to the x, that's going to give you ln 5 times what we started with. Okay? So we could take that one more step and say, let's say we have y equals a to the x, where a is a number. Not a variable, it's a number. 10 to the x, 20 to the x, half to the x. I know that dy dx, we just proved dy dx is going to be the natural log of a, remember a is a number, times the function that we started with, times a to the x. All right, well, let's say we had y equals a to the f of x instead, right? Well, we're going to do this the same way that we were doing the other ones. To find that derivative, we follow the rule that we just came up with here, but now we have something that's more gutsy in our exponent. So we're still going to get natural log of a times a to the f of x, but then we have to find the derivative of our exponent times f prime of x. A little confusing, I know, but just don't ever forget the guts. So let's do one more practice problem. If I have y equals, let's do 25 to the x squared plus 2, then I know my derivative is going to be the natural log of 25, whatever that base of my exponent is, times the function that we started with, times the derivative of the exponent. If you feel better putting these all in parentheses, that's totally fine, but not needed. Whew, that was a lot. All right, well, tomorrow in class, you are going to figure out how we're going to derive log base 2 of x using the math that you already know. There's nothing that you need to figure this out now. You already have the math that's needed to find dy dx. Okay? In fact, you could try it not right now and not look it up, and we can talk about it tomorrow. Have a great evening or day whenever you're watching this.